extremely brief class since we've gone over an exam and we don't have a ton of time left, but we'll get through at least a little bit. Happy project due day. I will handle any and all questions in office hours. I'll be around for a good chunk of the day, but I have a meeting from 12 to 1, but I should be free again at about 1 if you'd like to come back after my typical office hours to ask any questions or get some help. Last time we talked about we talked about enumerating both recursive and recursively enumerable languages. Recursive languages were a Turing machine could be built that can both accept and reject for every possible string that could be in the language or the star closure of the alphabet. We could determine yes or no in a finite number of steps, which means that there's an algorithm for it. It's great. A recursively enumerable language was one that we could say yes to. This string is in the language in a finite number of steps, but we can't say no to in a finite number of steps necessarily. So it's ambiguous between whether a Turing machine that has been running for some time on an input is going to eventually say yes or no, or whether it is in an infinite loop of some kind. So we found ways to enumerate both of those language classes where we could find, we can have a process that given any string that you could give me, I could answer at least whether it's in the language in a finite amount of time. I could say yes if the answer is yes in a finite amount of time, which is great. It allows us to at least isolate the strings that are in the language. But since that process is infinite, we can't ever, it won't terminate to the point where we say, if we didn't say yes, then the answer is no. So we can't ever conclude no if language is recursively enumerable. Then we last looked at languages that are not recursively enumerable using a very similar to Cantor's diagonalization proof for the couple of examples that we had for languages that are not recursively enumerable. So all real numbers and the power set of an infinite and countable set. So binary numbers were infinite and countable, and we found that that language, the power set of that, was not recursively enumerable. So we found this result that there are more languages than possible Turing machines, and that also allows us to conclude that some languages must not be recursively enumerable. Here are some interesting questions we might be able to ask/answer about fun. So the language is recursively enumerable. Does its complement have to be recursively enumerable? It's an interesting thought. If we wanted to negate all acceptance and rejection for a recursively enumerable language, would its complement be recursively enumerable? What do we think? Guesses? Who wants to say yes, it would be recursively enumerable? Who wants to say no, it would not be recursively enumerable? Split almost 50-50. I love it. The answer is actually no. And the reason for this, I have an intuitive reason. The book has the full mathematical proof by contradiction, but the reasoning is if you're going to flip yes and no, if you had a recursively enumerable language that we could not easily say no, the complement would not easily be able to say yes. So because of that, the complement is likely to be straight up not recursively enumerable outside of even recursively enumerable languages. This one is pretty straightforward. The answer should be relatively obvious. Are there languages that are recursively enumerable but not recursive? Are there languages for which we would be able to go into we would have to go into an infinite loop sometimes when the answer is no, the answer is yes. We've seen some of them. There were some examples of this. We saw things like what is a good example of this? Anyone want to give an example of a fun recursively enumerable language? We will see some momentarily. I think will be a good place to leave this, because I want to get to the universal language. The universal language is a set of encoded binary pairs, M and W. M represents a Turing machine, W is a string so that is accepted by that Turing machine. So it's all Turing machine string pairs where that string, when run on that Turing machine, is accepted. So the universal language is all possible accepts. If there exists a machine such that that string gets accepted, that pair is in the universal language. So everything that is accepted. Formally, M is an encoding of a Turing machine, W an encoding of a binary string. The question I have for you is, the universal language is recursively enumerable. How could we prove it? So this is an example of a recursively enumerable language. Any thoughts on that? How would you go about showing that the universal language is recursively enumerable? Let's talk about it real quick. All right. First thing we need to do, we need to construct a Turing machine that we're going to label the universal Turing machine. Its purpose is to recognize or accept the universal language. So we will think of this Turing machine as a multi-tape Turing machine where the first tape holds the input of the encodings of M and W. So we're going to use the encodings of Turing machines and binary strings that we developed a while ago. This is just they're in binary. So we break down the associated, here are the states, here are the transitions defined, all of that converted to binary. So there are just some binary string that represents a Turing machine. And there are many binary strings that don't represent a possible Turing machine. But we did say before that we could just enumerate all binary strings. Whenever we had a Turing machine, we could say, hey, that's a legal Turing machine. We'll throw it on the universal Turing machine's tape as a possible Turing machine. Second tape is going to simulate M's input tape. So when we find an M, the second tape is going to simulate that input. We initialize the second tape with an encoded form of W, which again we can find with regards to the star closure of the language. A third tape keeps track of M's state. So initialize the third tape with the start state. And when we make a transition on M, we can now simulate what M is doing on W from our universal Turing machine. Fourth tape can be used as scratch tape as we need additional space that we want to map to the cells of tracks 1, 2, and 3. So to simulate M, U is going to search tape 1 for a transition on the current state. The current state is stored on tape 3. The current tape symbol of M stored on tape 2. U will change the contents of tape 3 to record the new state. We'll change the tape symbol that is on tape 2 and moves the tape head for M left or right as specified by the transition of that Turing machine. And combined between these 4 tracks and this exact algorithm, we can emulate the behavior of a machine on an input string by doing this. So all we have to do now are find all such M and all such W and do this in a diagonalization very similar to the way that we talked about enumerating recursively enumerable languages. So we're going to simulate a single move on one, reset to the next, simulate a move, go back to the first one, simulate the second move, reset, make the third, continue this process for all such M and W, and we would have a way, some defined algorithm, to produce the universal language. So the language accepted by this universal Turing machine would be the universal language. And what's really fun about this is that U has all of the elements of a modern stored program digital computer. So it's doing everything that a modern computer can do, which is pretty amazing. Using this idea, we have now created an emulation for the modern computer off of a Turing machine. All right, we're going to come back on Monday and talk about why the universal language is not recursive. So why we can't be able to answer no all of the time to this. We can answer yes, that an MW pair, W is accepted by M, but what happens when W is not accepted by M? It could be that M goes into an infinite loop on W. So we will have proof for that coming. Have a good weekend, unless I see you in office hours, which means I can say have a good weekend after you get help on your project, or talk to me about your exam.
Interesting.